The title is Towards Scalable Learning-Based Optical Restoration. So here is her self-introduction. So Xing Huang is a second-year graduate student at Xiamen University, and her main research field is traffic engineering. So go ahead.
A learning-based algorithm that accelerates optical restoration. Optical transmission system transport traffic through fiber. We have an IP link between two routers and they are joined to one end of the IP link. We see that right after the router pulls, a device called optical transponder converts the signal from electrical domain to optical wavelengths. A NUC subsequently combines these wavelengths, which are then routed through a ROADM. On the fiber, amplifier is placed to compensate power attenuation during signal propagation. Therefore, an IP link is actually a logical connection supported by provision wavelengths. Operating a global scale one while maintaining availability is challenging, mostly because of unexpected failures, especially fiber cards. Historical fiber cards have triggered severe internet disruptions, causing significant society and economic damage. The question is, how do we solve this problem? The state-of-the-art approach published in SICAM 2021 requires a two-stage TE model that generates multiple physical optical restoration of light using random routing techniques for high probability failure scenarios and computes the optimal traffic allocation from the candidates for each traffic demand online using LP solver. However, we find three limitations of error. First problem is low scalability. As a pre-computation-based approach, error leverages fiber failure probability distribution to avoid the computer of failure scenarios. When low probability failure arises, error requires up to 2 hours to compute the recover solution on an optical topology consisting of 70 nodes. Second problem is implicit optical restoration. Let me take an example. There is a failure scenario in which fiber AD is cut, disrupting two IP links, AC with two wavelengths and AD with two wavelengths. One of error's candidate solution assigns two wavelengths to AC and only one wavelength to AD. However, the specific wavelength assignment to which path and which lambda remains unspecified. Third problem is limitation of candidate solutions. We derive a practical restoration strategy using an ILP model to get a specific solution based on the results of error. We found in approximately 16% of the evaluated scenarios, fewer than 20 of the 40 candidate solutions could be translated into practical optical layer configurations on Columbus, which constrains errors effectiveness in real-world deployments. And all the three limitations is because of current solution is dependent on the accuracy and efficiency of the ILP solver. To avoid the reallocation of traffic using ILP solver, we think machine learning is a good choice. And in the past 2 years, machine learning is applied to traffic engineering for multi-scenarios. Based on the learning algorithm, we can further accelerate optical restorations. Let me introduce the workflow of our system. The SDN controller first collects optical and IP layer topology information and layer mapping relationships. Then we generate various fiber failure scenarios to generate a trailing dataset and brain transfer model. each time a fiber cut happens. The model computes a restoration plan based on the current network states and deliver the updated IP link configurations to the SDN controller, followed by TE controller to generate the final traffic split ratio using a global solver. To further make sure the availability of the model, Lobs periodically retrain the model using the actual fiber cut scenarios. Let me give an example to introduce the training process of our model. There are 3 IP links, AB with 1 wavelength, AC with 2 wavelengths, and AD with 1 wavelength, and fiber AD is cut. Our goal is to restore the failed IP link as much as possible. At first, we compute the candidate restoration path for AD based on the k-shortest path algorithm. Then we feed the wavelength usage and candidate path as state. The path agent map the network state to the probability of k-shortest path and selects an available path to restore one of the wavelengths of IP link AD. And then the selected path is used as state observed by the wavelength agent, and the wavelength agent selects a wavelength to restore capacity for IP link AD. This separation reduces the complexity of decision-making process and makes it convenient to replace the fixed path set agent with an agent which can dynamically generate more optimal routing strategy in the future. And then the wavelength usage is updated based on the selected path and wavelength to make sure two agents know the first wavelength of path ACD is unavailable. We restore all wavelengths for all failed IP links. After that, we get an episode as trailing data, which also is a restoration configuration. And the return is the number of wavelengths that have been successfully restored. However, we found that in the trailing process, the model is hard to find the optimal solution due to invalid exploration. We propose a randomized assignment order for agents designed to promote more extensive exploration. Another technique is action masking to reduce the search space. We print the invalid path and invalid wavelengths to avoid invalid exploration. Our evaluation setup is as follows. As for baseline, we adopt two-phase solver as solutions from the ILP solver and error. We use 4 topologies from the Internet topology group as optical topology, wavelength distribution from error to generate IP layer topology. We generate the traffic matrix using the YANS. And our data set for training is 1500 and another 1500 for test. As for the matrix, our objective is to maximize total flow, and we normalize our results into satisfy demands. And our evaluation shows that LOPS significantly accelerates optical restoration. LOPS reallocate traffic within 1 second in larger networks with its primary computation bottleneck stemming from the LP solver in the larger topologies. Apart from being fast, LOP generates a near optimal traffic allocations. LOPs exhibit only a slight reduction compared to both solver and error. In conclusion, LOP demonstrates the ability to substantially accelerate optical restoration using reinforced learning, while also achieving near optimal traffic allocation. Looking ahead, we plan to explore extending this approach to more challenging scenarios, such as join routing and wavelength allocation, as well as join optical and IP network optimization. We look forward to sharing these future results in upcoming publications. Thank you for your listening.
Okay, so I have a question regarding your reinforcement learning modeling part. So if you, I'm really glad to see that you have a lot of performance improvements in the evaluation. And I'm wondering how large your data set is to train this reinforcement learning model to make sure that the entire system is performant as you show here.
Do you mean that how many training data? For a topology with 70 nodes, the training data is about 1 day.
Yes. Okay, then how many training samples you need to train the model? Because I know this is a reinforcement learning, but then how many iterations or like any more like quantitative data?
Our training set, the model, the size of the training data?
Yes.
I introduced it. About 15,000.
I see.
Yes.
So you generate the data yourself, or it's just public available in the data set? Because I'm not quite familiar with this entire problem, so I'm curious. Like, you generate the data yourself, or the public data set has the data?
Data set.
That's fine. I will ask a question offline. So just to give another round of applause for the speaker. Thanks.